Yes, but what we really did was observe what we did over here, right? We ideally wanted to sum over all possible paths, which would have taken an expectation over all possible paths, right? But then because of the linearity and because specifically of the way in which we computed the divergence, if the divergence had actually considered the entire sequence and kept the sequence separate, we were screwed, right? What happened was in the computation of the divergence, we ended up getting a sum of the divergences at individual times, right? And moreover, at each time, you got the probability of only one symbol, right? So this meant that I had this summation, and the summation itself only considered one term. As a result, this expectation could now move inside the summation, and now the sum over an exponential number of paths went away. Instead, what I got was that it's a single sum over time, and I'm just summing over the columns. So I'm just summing over the new table. That's it, right? And because of the manner in which we computed the divergence, this actually simplified matters a whole lot. Any other questions, guys? Okay, shut your laptops, the usual stuff, right? Let's start. Can you shut your laptop? Yeah. All right. So this magic term is the one that's going to be the single most painful thing you will encounter in this, second most painful thing you'll encounter in this course, the first being backprop. So let's go over this, right? What is this term? This computes the probability. So for every single symbol over here, it computes the probability that the best alignment, the most like the best alignment actually includes that box, right? That when you do the very best job of aligning this compressed simple symbol sequence to your input, you are going to find, for instance, that input 4 must be assigned to the phoneme B, right? That's what this guy is computing, this probability, right? So, or if you were looking at this one, this probability is saying what is the probability that the best alignment assigns input 3 to the phoneme E. In other words, that probability is going to be basically proportional to the probability of all possible paths that go through this box. Make sense? Right? So this term here is proportional to the probability of the subgraph that I have shown over here. Every path that goes through this particular box. This is key. Is that clear to everyone? Michael? Forget about the notation, right? So this term is the a posteriori probability. Remember how we computed the divergence, right? So if you go back here, because of the math, what happened was we were going over all time, and at each time you were going through this column and you're computing the expected divergence over the column, which is to say you are multiplying the divergence you would get if this was the correct symbol here by the probability that that indeed was the correct symbol, correct? So what we are really left with computing is what is the probability that this indeed is the correct symbol at that time, right? So for this to be for this highlighted box to be the correct, represent the correct symbol at time 3, it means you must ignore everything else that happens, so long as it is consistent with having this symbol at time 3, right? And which are all the alignments which are consistent with having this symbol at time 3? Those are all the alignments shown by the graph with blue. Anything else is going to not have the symbol E at time 3. Does that make sense? That makes sense to everybody, right? So this term here is basically proportional to the probability of this entire graph, which goes through the symbol E at time 3, or more generally, through the symbol SR, which is the rth row at time t. Right? Make sense? And this I can decompose into two subgraphs. So what I really want is the total probability of all paths in this graph. I'm going to decompose this into two subgraphs, everything to the left of the box, everything to the right of the box. Okay? Everything to the left of the box is the total is the graph that ends at symbol E at time 3. Right? This represents the probability of B aligning to S1, S2 as input 0 through 3. Right? You're saying I don't care how it is internally aligned. I want the last symbol at time 3 to be E. Correct? So if you extended it all the way to the end, that's basically the probability of the particular input sequence being aligned to the entire input, right? So this you get. This, what about the second graph? The second graph is the probability that this portion of inputs aligns to this sequence of symbols conditioned on the first subgraph. Make sense to everyone? Right? So all I've done is decompose this into two boxes. And once I do so, then I can do something simple. There's a lot of math, but the math basically says that in order to compute the probability of this entire subgraph, I can decompose it into the probability of this portion of the graph times the probability of this portion of the graph conditioned on this portion of the graph. That's a straight Bayes rule, right? But then here's where we're going to make an additional assumption. Right? I'm going to assume that the probability that the network assigns to the symbol E at time 4 does not depend on the probability that it assigns to symbols at time 3. Right? Is this strictly true? It turns out that in this particular model, because of the way we compute things, it is true, right? But there is no direct dependence, and we'll see why. So if I can make this assumption that the probabilities assigned at this time don't depend on the probabilities assigned at this time, then I can basically ignore these two edges and split it like so, right? Because there is no dependence, there's no conditional dependence. And then so I can say that the probability of this entire graph is going to be the probability of this blue graph times the probability of the red graph. That makes sense to everyone? Right? So, everyone, does that make sense to you? I see a question mark on your face. Okay. So how can I make this assumption that what the network what probabilities the network computes at time 3 does not affect the probabilities it computes at time 4. I can make this assumption because of the way we compute things, right? So think about this. Look at the dependency graph of how probabilities are computed. The input is used to compute the hidden values, right? The probabilities computed at each time only depend on the hidden values, and they're not dependent on the probabilities assigned at other times. If I've given you the complete H here, so when you draw the network, the way we actually compute it, you have this is x1, x4. These are the H's, and these are the Y's, right? The input is given. The input is deterministic. It was given to you, correct? So if the input is given, the computation of the H's doesn't consider the Y's, right? Giving the input is the same as giving this H, the hidden values, right? And because the hidden value is now a given, what is computed in this column doesn't affect what is computed in this column. Make sense? Right. What is the condition under which this would be violated? Yes. If I send the output back in, then the condition is violated, correct? But otherwise, this assumption is perfectly valid, right? And because of that, I can actually split this. I can split this box into two and ignore the dependence between the two, okay? So, and once I do that, then I can literally say that the probability of this portion of the graph is simply the product of the individual probability of the orange graph and the individual probability of the blue graph. Correct? And so I'm going to call this the forward probability, because it's the probability of everything from the beginning until here. I'm going to call this the backward probability, because it's the probability going back from the end until there. Okay? So because this is symbol r at time t, I'm going to represent it as alpha tr. And this is this graph that follows symbol r at time t. So I'm going to call this beta tr. So the tr indexes both the forward and the backward probabilities. Right? Now, how do you compute these? It turns out computing these is really, really trivial. Why? So first consider this forward probability, right? That's very simple. That's the probability of the subgraph. Okay? Now, it is the probability of total probability of all paths that start from here and end here, right? What are the different ways of ending over here? In fact, there are only two, right? I can either end up over here and then extend it, or I can end up over here and then extend it, correct? Make sense? Right? So the total probability of all paths that ends up over here is going to be the total probability of all paths that ends up over here times the additional score of extending it, plus the total probability of all paths that end up here, which is this guy, times the additional score of extending it. And the additional score of extending it is simply the probability of this node itself. Correct? So alpha 3e is going to be the probability of the subgraph that ends at 2b times y3e plus the probability of the subgraph that ends at 2e times y3e. Tony, make sense? Yeah, fine, right? If I see questions on your face, I'm going to ask you guys, right? I want this clear. So this simplifies my model, right? This computation is totally trivial. I can generally write this as, what is the total probability of the subgraph that ends over here? That's simply alpha 2b. Right? The same definition, correct? The total probability of the subgraph that ends here, that's just alpha 2e. See the recursion over here, right? Alpha is the total probability of a subgraph that ends at a specific node. And so the total probability of the subgraph over here, ending here, is also an alpha. The total probability of the subgraph ending over here is also an alpha. Right? So I can say alpha 3e is alpha 2b times y3e plus alpha 2e times y3e. Right? Or I can generalize that and say that the alpha for any tr, for the rth symbol at time t, is going to be the sum over all of the parents of that node of the alpha for all the parent nodes at time t minus 1 times y times the probability of the current node, ytsr. Make sense to everyone? Right? So once you see that, it becomes very simple, right? I can, in this particular case, there are only two parents, right? This term multiplies both equally. So I can actually start off by summing the alphas and then post multiplying the probability term in this particular case. And I need to compute, what I want to do is to compute these alphas for every node in the graph, okay? And so I'm going to start off by filling the first column. In the first column, the alpha for this guy is y0. I know that the graph doesn't begin at these other nodes, right? So I'm going to assign the probability of the alpha terms for these guys to 0, because there is no subgraph that ends over there, correct? Subsequent, so that's your forward algorithm for the first column. Subsequently, here's what we do. I'm going to go to the second column, and again, like in the case of the Viterbi, I'm treating the first row separately. But for each entry, I'm going to be summing the alphas for all of the parents and then multiplying it with the probability of the current node. Right? I do that going down this column, and then having computed the alphas for all of these guys, I can use these alphas to compute the alphas here. I can use these alphas to compute the alphas here, and do that all the way to the end of time, right? And so now I've computed the alphas all the way to the end. Make sense, right? Very simple. So here's the simple forward algorithm. I'm just creating the initial table, and you can see that as I only for the first time instant, you're doing something special. You're picking alpha 1, 1 to be the probability of the first symbol, and the alphas for the remaining entries in the first column to be 0. And then subsequently, this is just the simple loop, right? At each time, you're summing the alphas for the predecessors and then multiplying it by the current node probability to store it as an alpha, okay? And you can do this again without actually explicitly composing this table. It's just being shown, okay? So we've seen how to compute this guy, which is the alpha. I'm going to just sort of zap it down and call it alpha TR, okay? The second guy is now what we must compute. How do you compute the probability of this term? This can be done using the same logic, okay? Very similar logic. How so? We are interested in the probability of this subgraph, but then observe something very interesting, right? You want the probability of this subgraph, but it should not include this first box, because this first box was already part of the alpha graph, right? You want the subgraph that connects to this box. We are going to call that beta TR. And yeah, clear? Right? So you want the total probability of the subgraph that connects to this box, which I'm going to call beta TR, okay? And let's see how we can do this recursively. The subgraph that connects to this block, the total probability of the subgraph that connects to this block is the total probability of the subgraph that starts here plus the total probability of the subgraph that starts here. Make sense? Right? And those in turn I can extend out. I can pull this probability out like so, because remember, this is the total probability of this subgraph is going to be the probability of this node times everything that follows, right? So also the total probability of this subgraph is the probability of this node times everything that follows. So because these probability, this one is common, I can pull it out like so. So it's y4e times the total probability of all the subgraph that follows this node plus y4f times the total probability of the subgraph that follows this node. And this term is simply beta 4r for 1, and this is beta 4 2. See how that happened? Right? Because it's structurally the same. The total subgraph that follows this guy is structurally the same as the total subgraph that follows this one. So they're all just betas, right? And so I can write the beta for this box as this probability times the beta for this box plus this probability times the beta for this box, right? Or more generally, I can say the beta for any box is the sum over all the successors of that box of the product of the probability of the box and the beta for the box or the node. Another question? Except you're summing things. In the backward, it's slightly different, right? You're doing it backward.
I understand why we're doing it forward. We want to see how we end up at this symbol given all of the possible previous sequences. But what's the reason for doing backward?
Because you want the total probability of the entire subgraph end to end. Right? Yes. Okay, we are saying what is the probability that this symbol was in the alignment? That's going to be the total probability of all paths that go through the node corresponding to that.
Why can't we just keep forward?
Because then you're ignoring what happened in the future. think of this, right? The question we are really asking, going back here, is what is the probability that the correct alignment at time 3 was the symbol E, given that this is how many inputs you've got, and this is the complete symbol sequence. This means you must consider everything before and everything after. Makes sense? You don't look convinced?
No, I think I understand what we're doing now, because we are aligning it, not just finding the sequence from where we were looking.
No, we're saying what is the probability that this guy, somebody has said all of this, and here is the recording. What is the probability that at time 3 he said the phoneme E, considering that he's also said things afterwards, right?
Yeah. So he was aligned at, what's the probability that he was aligned at time T?
What is the probability that he was aligned to E at time 3 or at? Right. Okay. So anyway, going on, here is the backward probability, right? So once we get to this backward, the rest is kind of fairly prosaic, right? So how can you actually compute the backward probability? I'm going to assign the backward probability to this guy as 1, because the subgraph that follows this is, there is no subgraph that follows this. But I do know that the final observation cannot be from these nodes. So I'm going to assign a beta value of 0 to those guys. And then I'm going to go back and I can use the beta terms here to compute the beta terms for this column using the arithmetic that we just saw, right? Where for each node, I am summing over both of these successors, and what I'm summing is the product of the beta for the successor and the probability at the successor node, okay? And I can compute the beta here, go back, take a step back, keep going backwards until I compute the betas all the way to the beginning. And so now at each time, I have both an alpha and a beta, correct? So this is the simple backward algorithm, just in pseudocode. Right. So this term has also been computed. The probability of the blue graph was the beta term. We've computed it. I'm going to represent it like so. Now the product of the alpha and the beta is in fact the probability of this graph conditioned on the input, but it's not conditioned on the symbol sequence. There's a joint probability of the symbol sequence and the input. That's because the network is actually also producing probabilities for other symbols, correct? So if you compute the total probability of this box, it's not going to be 1. It's going to be something else, which means we must normalize to make the whole thing sum to 1, right? Anyways, so if you want the a posteriori probability that this was the correct alignment at time 3, then it's going to be proportional to alpha times beta, because alpha is the leading portion of the graph. Beta represents the probability of the trailing portion of the graph, so it's proportional to the two. And to make the probabilities for the entire column sum to 1, you just have to normalize by summing over, by dividing by the sum of the products over the column, right? So the total probability of the graph that goes through this guy is alpha times beta. So you would normalize by the sum of alpha betas over the entire column. And that is the a posteriori probability of this node. And I'm going to represent that using the symbol gamma. So it's gamma times t comma r. So this was the most painful portion of this lecture, okay? I'm assuming that you got it. It wasn't particularly hard, right? Michael, makes sense, right? And so this is just the pseudocode for it. Let's see how this affects our divergence, because this is what we were doing, right? Our divergence was computing the expected divergence over all possible alignments. But then when you tried to do that, you ended up summing over all time and computing the expected divergence across each column of this graph. The expected divergence, of course, had the log probability for each box, but that had to be weighted by the posterior probability, which was just gamma TR. Okay? And now, when I'm performing back propagation, this is what I must differentiate with respect to the outputs of the network. So when I'm differentiating with the divergence with respect to the outputs of the network at any given time, I'm going to be computing the derivative of the divergence with respect to the probabilities assigned to each symbol at each time, right? And since for any given time I can ignore the summation over time t, I just have to focus on these terms must be computed from here, which is to say that I can ignore t, I can just focus on this one column, right? And consider the derivative of the divergence with respect to any one symbol. The derivative of the divergence with respect to, say, E is simply going to be the derivative of this term computed but then E occurs twice, right? So I'm going to be summing this derivative can be, the divergence can be computed in two locations, once here and once here. I'd be summing the two. So I'd be summing over all rows which represent the same symbol. And summing that, and this is the sum divergence over all rows that represent the same symbol, and it's the derivative of that guy that I really need. And computing the derivative of this term is the derivative with respect to the output, with respect to the probability assigned to the symbol at time t by the network. That and the term whose derivative we are computing is gamma times log y, right? Which is going to be, focus on that, it's gamma divided by y plus the derivative of gamma times log y, right? Straight up chain rule. And typically the second term is ignored. So if you think this is the correct way of doing it, if you're thinking of finding the expected divergence over all alignments. But if you want to wave your hand a bit and call it a maximum likelihood estimate, then you can ignore the second term, which ends up becoming a little painful, right? And so the approximate derivative is simply the ratio of the gamma at each time to the probability assigned to the symbol at each time, right? Which makes the entire derivative very simple, right? The derivative of the divergence with respect to the probability assigned to any symbol at each time is simply going to be the sum over all instances of that symbol in the column times the gamma assigned to the symbol divided by the probability assigned to the symbol, minus of that. So, yes, Michael? Yeah. So because the network produces a probability for every symbol, including symbols that are not in the target sequence, right? The rows are not the entire set, correct? So it's not one. That's why you have to normalize. So once we've done this, the rest is easy. The rest of the lecture is kind of fairly straightforward. There's one extra kink that we'll have to deal with, but I'm assuming that you got this so far, right? So we know how to compute these divergences. And so we know how to compute this guy, right? So you know how to compute this guy. And once you know how to compute the derivative of the divergences with respect to the output at each time, you can just use backprop and train the network. So the overall process is going to look something like this. You're given an input and output sequence without alignment. We have to train the models. So you set up the network, typically a many-layered LSTM. You initialize all the parameters. You compose this graph, right? And first, you pass the network for training instance through the network and compute the probabilities for all the symbols at each time. Then compose the reduced graph, the table. From this one, you perform the forward-backward algorithm to compute alpha and beta at each time. And then from the alpha and beta, you compute the gamma at each time. Using the gamma, you compute the derivative of the divergence at each time. And then you can use that, which is this guy here, right? And then you aggregate the derivatives over the mini batch and update your parameters. Very straightforward. So story so far, I have just a little bit to go, but I have many slides, mostly animation. So the sequence-to-sequence models which irregularly output symbols can be decoded using Viterbi decoding. They require alignment of the output to the symbol sequence for training, which will often not be given. So the training can be performed by iteratively estimating the alignment and time synchronous training, or it can be performed by optimizing the expected divergence over all possible alignments, right? So far so good. We have left one key issue out. What happens if you have repeating symbols, right? So let's say an aligned output was this guy, RR, 4 O's and a D, right? Or a couple of D's. Does this represent the word rod, or does this represent the word rude, both of which are valid words in the dictionary, right? Now, there's no way of knowing from this guy which of these two it's going to be. So we need an extra artifice, and what we will do is, again, we've seen this before, right? You cannot distinguish between an extended symbol and repetitions of the symbol, right? So what we are going to do is to introduce an extra symbol, which we will call a blank, who has only one job in life. The blank doesn't really have an existence of its own. Its only job in life is to separate repetitions of symbols. Basically, when I take an alignment, I can compress it to the compressed sequence, right? I compress all the repetitions of the sequence. But if a blank occurs between two instances of a symbol, I cannot collapse it. So for example, this guy, RRR, blank, 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 OO, blank, blank, DDD, when I collapse it, the sequence of R's is going to become the R, symbol R. The blanks disappear. The sequence of O's is going to become O, and the sequence of D's becomes D, right? On the other hand, if I have something like this, which is RR blank R, when I collapse it, the first two R's are going to become an R, but then there's a blank which separates the two instances of R. So I'm going to get two R's, a single O, and then again, because there's a blank between the D's, I'm going to get two D's. Make sense, right? So, or for this guy, what's this going to become? It's going to be R, 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 O, O, D, D, D. See how that happens, right? So we've actually introduced a separator, a blank. The blank is a nothing operator. All it does is to separate repetitions, repeated instances of symbols. But now the blank must be recognized, right? So what we will do is to introduce an extra blank, the blank, as an extra symbol in your vocabulary. So instead of just having the standard symbol set, you're going to have the standard symbol set and an extra blank. Yes?
So if you go back one slide, when you look at how many blanks there are, how do you distinguish between 3 blanks and 2 O's?
So it doesn't matter. The blanks just disappear. You throw them away when you collapse the sequence. The blank disappears, right? The blank is a non-existent symbol. It's a blank, or it's a nothing symbol whose only job is to separate things, right? It's like saying nothing happened here, but the events on two sides of this nothing are different.
And that's true also when you're trying to train the network with the divergence.
So we'll see how that affects things, right? So I'm going to introduce this blank, but then this makes things a little tedious. So consider this. Suppose this is my best decode, never touches the blank, right? So these two B's can be collapsed to B, these two E's can be collapsed to E, these two F's, these three F's can be collapsed to F, and then this E is E. So this is beefy, right? But on the other hand, if I had a decode like this, I can have the initial blank goes away. This is going to be B, E, and then these blanks don't matter. It's still phi, right? But here I have B, I have E, then there's an F, and there's a blank between the two instances of F. So now there are two F's, right? So introducing this blank means you're going to have to change a few things, right? Earlier, when we just collapsed our, okay, I've changed my example. I made my two E's follow one another, so this is B, E, E. This is not even a word. It's just my example. I need a better example. Anyways, so we were just pulling out the rows and patching them together, correct? When we were training the model. You can't do that anymore. What you have to do is to account for the blanks, right? So you're going to introduce a blank between every 2 rows. And the way you will do it is to pull out the blank row from the output of the network and insert it repeatedly between every 2 symbols, and before the first symbol and after the first symbol, because a blank is allowed to occur in the first location, because when you compress things, the blank goes away, right? And so, but then when you do this, you end up with a little trickiness. Why? I can't just compose the graph left to right as usual, right? What happens? I'm allowed to go from a symbol B to the symbol B. I'm allowed to go from the symbol B to a blank. I'm also allowed to go from the symbol B to E, right? Because a blank can occur between a B and an E, right? But I'm allowed to, the first and last columns are allowed to end at initial and final blanks, right? For skips are permitted across a blank, but only if the symbols on either side are different, right? So here, for example, I have 2 E's. If I permitted a skip, then even though I'm trying to align a double E, I wouldn't be able to the alignment wouldn't introduce a blank between the 2 versions of E. So I'm forcing a blank between the 2 copies, 2 sub-instances, the 2 instances of E. Make sense? Right? So we've added some new rules. A blank can only go to the next row, right? Because you can't skip from a blank to the next blank. You can't skip a symbol. You can skip a blank only if the symbols on either side of the blank are different. And that's about it. So that means that when you actually compose this graph, you get these extra blue arrows. Is that here?
So I guess I understand the point between putting the blank between like the 2 indices of E, but what is the point of putting it in between like E, like the E and F?
E and F. The point is the blank is a know-nothing symbol, right? So the way we define it, go back and look here. I have too many slides. Okay, look at this guy here. I can have an OO blank in D, right? It means that, and this too becomes OD, right? So this means blanks are allowed between 2 different symbols. Yeah, just ignoring it, right? So I can either have OD or O blank D, and they both represent the same thing, which is why I introduced the blank.
In this example, we have multiple blanks, in consecutive ones, but we just disallowed it with the...
No, we didn't, right? So observe this. I have horizontal edges. So meaning a blank can always be followed by a blank.
Oh, but just not like this.
I can't skip from 1 blank to 2 blanks aside, right?
Also that we do not want to skip the middle one.
You don't want to skip the symbol. Yes, Michael.
One part that is not allowed in this graph is the B, then E, then directly to F.
So B, I'm not allowed to go from B. I can go from B to E. I can't go from 1 E to directly to F, because then I'll be skipping the second E, right? I'm ensuring that every path through this, when collapsed, gives me B, E, E, F, right? And this is the only way I can ensure it, but it's a very simple rule, right? Once I've composed this graph, the rest of this becomes simple, right? So this is the composed graph. Observe that all I'm doing is, when I'm pulling out everything and composing the new graph, I have this extra flag which tells me whether the next thing can be skipped or not, okay? And now I can actually do a Viterbi alignment on this extended graph, right, with the blanks. Or I can do the forward-backward, right? For the forward-backward, come on. Something happened. It's telling me the class is over. Yeah. Close. My battery is running low. Okay. I can do a modified forward algorithm. The forward algorithm is now going to use the new graph. Okay. And the forward algorithm is basically going to use the new graph like so. Observe that when I'm computing the forward, I have to check if the current symbol is a blank or if the current symbol is the same as the previous symbol. If that is the case, then I have only two parents, right? But if the current symbol is not a blank, for example, F, guys in the row, F row, nodes in the F row have three parents. Nodes in the blank row have only two parents, right? So also nodes in this E row have only two parents because you're not allowed to skip from the E to the previous E. So I'm going to have to make adjustments for this guy when I do the forward algorithm. So the forward algorithm would be like so. In the first column, if I begin going left to right, I'd be putting the symbol probabilities in the first two entries. The rest would become 0, and then I can just run the forward algorithm going forwards. And so also in the backwards, by the way, guys, that's the URL for signing up for today, okay? I'd be putting once in the final two symbols, and then I'd be going backwards from there, okay? And just use the backward algorithm going backwards. So the overall, now in the backward, once again, here is the key piece. If your current symbol is either a blank or it's the same as the next symbol, then you're only summing over two successors. Otherwise, you actually will have three successors, right? And so I think I've run out of. Amazing. So I will actually record the rest of this lecture because I'm out of battery, but which will probably take about 15 minutes of my time. I was too slow. But this piece, there's a key component that we will have to record, which has to do with beam search, and I'll put this up. So we will continue here from where we left off in the morning. In the morning, we saw how we could introduce a blank symbol in order to account for repetitions of a symbol in a sequence, in a compressed sequence. And we saw how we would have to modify the graph in order to account for the blank symbol. The way we did it was as shown over here. Instead of merely having the symbols by themselves, we alternated the symbols with blanks. And when we composed this table, every alternate row was the score, was the row of probabilities computed for the blanks by the network. And the graph we composed, of course, had the structure where you could have horizontal transitions within any row. You could transit from a blank to the subsequent symbol, but not to anything afterwards. From any given symbol, you could transition to the same symbol. You could transition to the subsequent blank. Or if the next symbol was not the same as this one, you could transition to that symbol. In cases like this E, where the next symbol is also an E and the blank is used as a separator to distinguish between two instances of the E, the transitions here, the transitions allowed are the transition into the same row and the transition into the subsequent blank. Now we will perform the backward computation on this graph. We start off by assigning a beta value of 1 to the final two rows in the table. Then again, observe that the final row represents a blank because after the final symbol, you can have an unlimited number of blanks in the aligned sequence before you compress it. So the final row is a blank, and we're going to assign a beta value of 1 to the final two nodes in the graph, and a beta value of 0 to all the nodes which have been marked in black. So that's what this equation shows. You see that at time t minus 1, which is the final instant. For the final row, which is index 2k minus 1, now why 2k minus 1? That's going to be if you're alternating every symbol with a blank, then if you have k symbols, then you're going to have 2k rows plus the final row, which is the blank row. So the index is going to be 2k minus 1. So for the final row, which is beta t minus 1, 2k minus 1, which is this box, we assign a score of 1. And to the previous row, which is actually the final symbol in the sequence, BEEF, that beta 2 is assigned to 1. And all other betas up here are set to 0. Subsequently, we will work our way backwards and compute beta for every row going back. Now, as you go backwards at any row, if you happen to be a node in a row from a blank, there are only, as I mentioned earlier, there are only two possible successors. So the beta at any node is computed as the sum of the beta in the same row at the next time instant multiplied by the corresponding probability plus the beta in the next row at the next instant multiplied by the corresponding probability. So for in any row corresponding to a blank, the beta TR is obtained by summing over two beta values. One is the same row itself at the next time instant, and the other is the beta at the next row. Similarly, if you happen to be in a row like this E, where the next symbol is also an E, then there are only two possible successors, the same row and the next row, because you're not allowed to skip down. And so once again, the beta is going to be computed from the beta in the same row at the next instant and the beta in the next row. So beta TR is going to be beta T plus 1 R times this probability plus beta T plus 1 R plus 1 times this probability. On the other hand, for other rows like the second E or the B, or where the next symbol is not the same symbol as this one, you actually have three successors. So you can either transition horizontally or go into the subsequent blank or skip the blank and go into the next symbol. So now you must actually sum over three beta values to compute the beta up here. There's a special case, which is the second row. And the second row, once again, has only two successors. So when you write your logic, you're going to have to deal with that row as a special case. So here is the overall algorithm, pseudocode, which is somewhat incomplete, as you will see when you actually check it out. But there are two special cases. The first is the last row, where there's only one possible successor. Second special case, which has not been explicitly that has actually been handled over here, is also one where there's also one where you only have two possible successors, and in all other subsequent rows, you're summing over three beta terms. This is just a simple backward computation for the betas. Now, once you perform both the forward computation and the backward computation, then the rest of the computation proceeds as follows. You can compute posteriors and derivatives exactly as before, but now you're going to be using the extended sequence with the blanks. So here is the algorithm for computing the posteriors. As before, at each location in the graph, you multiply the alpha and the beta values, and finally normalize the product to compute the posteriors, which we designate as gamma. So the derivatives are going to be computed as before. The derivatives are simply going to be, in any column, are simply going to be the ratio of gamma to the symbol probability. So the overall training procedure is as follows. You're given input and output sequences without alignment, and we must train models. So as a first step, we set up the network, typically a many-layered LSTM. You initialize all parameters of the network. You include a blank symbol in the vocabulary. This is the key piece. And then subsequently, for each training instance, you would pass the training instance through the network, and the outcome is going to be this matrix of probabilities, where each column gives you a probability distribution over all symbols given all inputs until that time. This matrix includes probabilities assigned to the blank symbol. Then in the next step, you would construct this graph for the input. This forward pass is going to be computed for each training instance. And then in the next step, you would compute this graph for the training instance from the probability table, and then perform the forward and backward algorithms to compute the alphas and the betas at each time for each row. and subsequently compute the gammas, compute the derivative of the divergence for each output symbol. And once you have the derivatives, which, as we saw earlier, is going to be simply the vector of derivatives of the derivatives of the divergence with respect to the probabilities assigned to each symbol, you can aggregate the derivatives over the mini batch and update the parameters. Fairly straightforward. I recommend you go through the pseudocode to get a good handle of exactly how this is computed, but the logic is not particularly complex. This overall framework that we saw is referred to as CTC, or Connectionist Temporal Classification. This applies when duplicating labels at the output is considered acceptable and when the output sequence length is lesser than the input sequence length. So again, you're speaking of order synchronous but not time synchronous outputs, where an integral component of the problem is to determine the alignment of the output sequence to the input sequence. So there's one final bit that we must consider, returning to an old problem, and that is decoding. Now, earlier we saw that you can just, when you have a test sequence as input, we want to obtain the corresponding compressed sequence. We saw that there was a simple technique of doing this. You could just compute this probability table for the test sequence, and within each column, you could just pick the most likely symbol. Now, this can be applied directly. This is going to give you the most likely time synchronous sequence. Now, the problem we had earlier was that in an output such as this, you couldn't distinguish between repetitions of a symbol and a single instance of a symbol. But once you introduce blanks, this actually automatically gets handled. So you can just perform your regular Viterbi decode, and you will get a perfectly decent output, which gives you a sequence that can be collapsed into a unique, non-ambiguous, compressed, order synchronous symbol sequence. And it turns out this works really nicely. And one of the reasons is that the blank symbol ends up capturing a lot of slack, and you get this and captures the notion of no transition happening here. So anytime the alignment does not require the transition of symbols, what ends up having the highest probability is usually the blank. So the upper row in this figure, this is a figure that I got from Alex Graves' paper. They showed two different instances of decoding. The upper row is what you get when you don't have blanks. And you can see that in this region, the symbol is S. And you can see that the probability for S is high through the region. And because there's no blank, you have no way of knowing whether this is a single S or multiple S's. Now, here is what happens when you have blanks. And observe that throughout the decode, the most likely symbol at almost all times is the blank. And the actual symbol itself only pops up specifically at the transition location. So you naturally get this behavior where the symbols only become very likely around the location where they must be hypothesized, which is to say at the end of every sequence of every segment corresponding to that symbol. So it naturally gives you not only an ability to obtain unambiguous alignments, but also gives you this behavior where the output actually looks like what we are looking for, which is a sequence of blanks followed by the appropriate symbol peaking at the right times. Regardless, you have an issue. What we want to find is the most likely order synchronous but not time synchronous symbol sequence. So if you have a sequence of inputs, a sound recording corresponding to the word red, you only want the output r, e, d, and you're not worried about the exact alignment of these symbols. You want to find the most likely compressed symbol sequence without Also wanting it to be the most likely time synchronous aligned sequence. We saw the distinction between these two earlier in the lecture when we were talking about the decoding process, right? So what Viterbi finds is going to find the most likely time synchronous symbol sequence. It's going to find something like this: R R R A D, and you have to compress it. And we saw that the most likely time synchronous sequence need not necessarily correspond to the most likely order synchronous sequence. So what we want to find is the symbol sequence for which the probability of the symbol given the input is largest. So if you have an input which is some 10 symbols long, let's say x0 through x9. So there are many possible sequences over here. Assume you have 3 symbols A, B, and C. You can have the output could be just A, it could be AB, it could be ABC, and so on. It can have the symbol sequences could be just 1 symbol or up to 9 symbols long. And of all of these symbol sequences, you want to pick the one symbol sequence which is most probable. So you want to find argmax over S, P of S, P of S given X. You want to find the symbol sequence which is most probable given the input. But the problem here is that computing this is hard. Now, what exactly do I mean by the probability of a symbol sequence given the input? We've already dealt with this. So let's say I have 10 inputs, and let's say I'm considering the symbol sequence AB. The actual graph you would have to consider is going to be, must also consider blanks. And so here is, let me actually draw the entire thing just to be precise. And I'm going to assume for now that there are only 1, 2, 3, 4, 5, 6, 7 inputs for simplicity. So here is the graph. It's going to be this. I can have the A going forward, this blank going forward. I have all of these arrows. Then from A, I can go to a blank. From A, I can also go, I can go to a blank here. I can also skip to B because A and B are different symbols. And then from B, I can skip to a blank. So this would be your entire graph, would it not? So, and so this is not the entire graph yet. I'd have to draw a few more edges, but you get the idea. And so this is going to have this graph. The alpha probability out here represents the total probability of all paths that start at either of these locations and end up at this node. The alpha probability over here represents the total probability of all paths that start in either of these locations and end up at this node. And the sum of these two alpha probabilities is the total probability of the symbol sequence AB given this sequence of inputs. Now, if you want to perform a full forward decode, what you're really going to need to do is to compute this probability, P of S given X, using this graph for every symbol, every single symbol sequence, which means that if you want to pick the best of all of these choices, you would have to compose this graph for ABC and compute the forward probability at the end. Then you'd have to compose the graph for just A, compute the forward probability at the end. Compose the graph for the sequence AB and compute the total forward probability at the end. Now there are an exponential number of such sequences and every one of them must be evaluated. And you're going to have to pick the most likely symbol sequence by constructing the graph separately for every one of these guys, computing the final forward probabilities at the end, and then picking the graph and the corresponding sequence for which this probability was highest. Clearly, this is not going to be feasible because it's exponentially complex. So the computational complexity is exponential. Now, how can you do this? So here's a statement again. Explicit computation of this guy is not going to be feasible. You want to compute the alpha probability for every single symbol sequence, and you want to pick the symbol sequence for which this alpha probability is highest, which means we're going to have to compose this graph for every single symbol sequence and then compute the alpha from it. That's not going to be feasible. But it turns out that there is a heuristic which allows you to do this reasonably well. And the idea is to organize all possible symbol sequences as some kind of a tree. So how exactly does that work? Consider just two symbols. Let's say I only have S0 and or S1 and S2, right? Now, let's take a sequence of just two symbols, S1, S2. What are the different ways in which I can do it? I can do blank S1, S2. I can say blank S1, blank S2. I can say blank S1, blank S1, right? Then again, I can have S1, S2, S1 blank S2, and S1 blank S1. All of these, when compressed, are a sequence of only two symbols. And in every single case, so this is going to become S1, S2, right? This is also going to become S1, S2. This is S1, S1. This is S1, S2. This is S1, S2. This is S1, S1. So these are all different ways in which I can just expand these sequences. And these are the only two sequences which begin with S1 that I can generate. Now, let me represent all of these most compactly. The first symbol could be a blank, right? And from the blank, I can go to an S1. So this blank is optional. I've accounted for these blanks. And once I account for these blanks, this block is identical to this block. After an S1, I can either produce an S2, which is this one, or I can produce a blank and then an S2, which accounts for these guys, or I can produce a blank and then an S1, right? I can do the same thing going down, and if I wanted to consider all possible two long symbol sequences which begin with S2, my first symbol could be S2. Then the next symbol could now be an S1, or I could have a blank S1, or I could have a blank S2, right? This little tree-like structure, it's not really a tree because you have this, it's directed, but here you have this thing folding back, and so you have two incoming edges into this node. But this little tree-like structure represents all possible ways of generating a two-symbol long sequence. Now, in the process, what I have not explicitly shown is that when I have an S1, this S1 represents an arbitrary number of repetitions of S1, okay? But if you ignore that, then this represents the entire structure, which represents all possible ways of producing symbol sequences of length 2. Now, if I want to have a symbol sequence of length 3, then again, I'm just going to have to replicate this little structure from here. So this is going to be blank S1, blank S2, and then S2. From here, it's going to be S2 can go to either S1, or it can go to a blank and then S1, or it can go to a blank and S2. And similarly, these two would also be extended. And so the overall structure is going to look in that case. The overall figure is going to be like this if I'm considering symbol sequences of up to length 3, and I can keep extending this tree forward if I want to consider longer and longer symbol sequences. Now, how does this help us? This figure to the left over here represents the tree that I showed you in the earlier slide, which is this guy, except I've sort of flattened it and drawn it vertically. So I have a connection from blank to S1, blank to S2, then S1 goes to its own little subtree, which is colored green. S2 goes to its own little subtree, which is colored pink. And then you can keep extending this upwards. Now this figure here is a graph, which is very similar to the graph we composed or considered for performing the forward and backward algorithms earlier. And except with one simple difference, that when we composed these graphs earlier, the graph was drawn top to bottom. Now I've just sort of changed the direction. I'm drawing it bottom to top. And how this figure is constructed is that I'm going to sort of unroll this graph over time. So between any two columns, I have nodes corresponding to every one of these symbols. So basically, so each row over here represents all the nodes corresponding to one symbol. And between any two columns, I will have a connection between two nodes if there is a connection shown over here. Now, if you will recall the kind of graphs we drew for the forward algorithm, that too followed the same logic, although I may not have stated it explicitly at the time. So this graph basically shows you the various ways in which I could produce a symbol sequence. So if I wanted to produce S1, I could produce just S1. I could produce a sequence of blanks and then an S1, or a shorter sequence of blanks and then two S1s, or two blanks and three S1s, or just start off at S1 and go all the way to S1, right? So similarly, if I wanted to just produce S1, S2, then any path which, when collapsed to the left, does this, which goes from here to S1 and to S2, or from here to blank and then to S2, is going to represent a path that, when compressed, becomes the symbol sequence S1, S2. So this graph has this property that every node in this graph represents a unique symbol sequence, meaning if you start from this node and work your way backwards to the initial portion of the graph, the first column, there may be multiple paths from this node to this first column, but every one of the paths, when collapsed, is going to give you a single symbol sequence. And so the set of all paths to this particular node from the beginning gives you all possible ways of producing that particular symbol sequence. So if I compute the alpha values at any particular node, that alpha value is going to give you the total probability over all possible alignments for that symbol sequence. So the alpha value over here is going to be the total probability of the symbol sequence S1, S2 having been produced over 4 time instants. Now the alpha, of course, is going to require you to compute, symbol probabilities at each of these nodes, and those symbol probabilities are going to be obtained from the network, right? So all you have to do is to construct the tree as we have over here, and then flatten the tree as shown up here to the left, and then compose the graph, the trellis that we have to the right, and then perform the forward algorithm on this trellis. And when you get to the end of your input, you're going to have alpha values for every possible symbol sequence that you could have had in those many time instants. And now, if you want to find the most likely symbol sequence, all you have to do is to pick the symbol sequence for which the alpha value is highest. So the problem, of course, is that as you keep growing forward, the number of rows increases, and it's going to increase exponentially fast because the number of possible symbol sequences increases exponentially fast. So we haven't actually simplified the problem. We've just sort of come up with a way of representing all possible, representing all the graphs for all possible symbol sequences in one compact way. But this does give us a way of doing this in a computationally acceptable manner. What we will do is to start from here and begin performing the forward algorithm going forward. But at each time, you're going to have a certain number of nodes that have been computed. We will pick the most likely node, and then we will keep some k most likely nodes in the graph and delete the rest of them from the graph. And then only continue to extend the graph from the nodes that remain. So if you do this, the final decode is not necessarily going to be the most likely one, because we are introducing this heuristic of pruning, which is likely to lose some important paths, but it makes the whole thing computationally feasible. So one of the things that helps us in this and keeps this thing from getting too suboptimal is the fact that CTC scores peak at symbol terminations and tend to have low values for anything other than blanks at locations which are not clear symbol terminations. So which means that the graph, even though the graph gets larger, the number of paths with significant scores typically remains small. So rather than try to explain the whole thing from using just the figure, I'm going to try to explain it using a little bit of pseudocode. Now, and so we have some beam search pseudocode. This will also figure in your homework, so please pay attention and then go back and look at the pseudocode yourself on the slides. And if you don't get it, then the first recitation after the break is going to go over that in some detail. So what we will do is to retain separate lists of paths and path scores for all paths that are terminate in blanks and those that terminate in valid symbols. So if you go back over here, you'll observe that some rows represent a path that terminates in a blank. Some rows represent a path that terminates in a symbol. So we're going to keep separate lists for both of these. And here is the entire beam search algorithm. Now, I won't actually go over this right now. Instead, let me just spend a little time going over this one step at a time. So consider the very first command over here. So that is merely computing the node scores at these nodes. If you have some k symbols, then you're going to be computing node scores at k symbols plus the blank. So these scores are being computed, and you will initialize the paths which end at blanks with just this one guy, and the paths which end at non-blank symbols with these two guys, because there's a path which ends here, there's a path which ends here, and there's a path which ends just here. Subsequently, you have a collection of paths. You're going to find the most probable one, and then you're going to retain, say, the k most probable paths, and you're going to delete the rest of the paths. This is pruning. And so you have this pruning step where you find the most likely path or the k most likely paths and delete everything else from your lists. Having done that, so you then extend all paths that will end at blank. So in the tree, if you're at S1, you can extend this path into this blank. If you're already in the blank, you can extend the path and remain in the blank. So extension with blanks corresponds to transitions which are shown by these green edges in this graph. You also correspond to horizontal transitions at blank nodes itself. So here's what happens. You're going to be computing, so let's say you're at this time instant. You're going to extend all paths which go into the blank rows at the next time instant. So you'll be computing this guy. You're going to be computing this guy, and summing the two over here. You're going to be computing this guy, and summing the two scores over here. So that is the extension with blanks. Subsequently, you're going to be extending with symbols, which means that you're now going to be extending all paths into nodes that arrive at symbols. So if, say, you're an x3 at time 3, you would be computing this, and computing the sum score over here. So you'll also be computing this, and this, and this, and computing the sum score here. This is a blank, so you wouldn't do anything here. You'd be computing the sum of these 3 incoming paths for this node, the sum of these 2 incoming paths for this node, the sum of these 2 incoming paths for this node, and these 2 incoming paths for this node. So the extend with symbol is going to basically compute the scores for all nodes, which correspond to a symbol sequence that terminates at a symbol. And so these little little pseudocodes actually represent the implementations of each of these extensions. I'll skip them, including pruning. And then finally, let me go back here. Something interesting happens. Once you're done going all the way to the end, you will find that, let me go back a couple of slides to make this obvious. Consider this guy. If you want to consider the symbol sequence S1, S2, you have alpha S1, S2. Wait. S1, S2 is not a good example. Just consider the symbol sequence, which is just S1. So you have alpha S1. You also have alpha S1 blank. S1 and S1 blank represent the same symbol sequence because the terminal blanks don't really count, right? They're blanks, they disappear when you compress them. So which means that if you want to compute the alpha for the symbol sequence S1, you must actually sum the alphas for these 2 guys. So also if you want to compute the symbol alpha for the symbol sequence S2, you must sum the alpha S2 and alpha S2 blank. If you want to compute the alpha score for S1, S2, you would be summing the alpha for S1, S2 and S1, S2 blank, which is not shown. So this merging is what we call the merge identical paths out here. Once you've gone through the entire graph and you've computed the alphas for all symbol sequences at the final time, you would merge all identical paths and then just pick the path which has the highest score. So the actual pseudocode for every one of these operations is shown on the slides. Please look over them. I won't actually go over them in the lecture, but they should be self-explanatory, and if you have any problems, please post in Piazza. So once you've done that, you can just pick the most likely path, and that is your beam search algorithm, where instead of just doing a Viterbi decode and finding the most likely time synchronous sequence, now we are actually finding the most likely order synchronous sequence, where in computing the probability of any sequence, you're computing all possible ways, the total probability of all possible ways of aligning that sequence to the input. And so, getting to the end, the story so far is that sequence-to-sequence networks which irregularly produce output symbols can be trained by iteratively aligning the target output to the input and time synchronous training, or optimizing the expected error over all possible alignments, which is what we call the CTC training. Distinct repetitions of symbols can be disambiguated from repetitions representing the extended output of a single symbol by introducing blanks. Decoding the models can be performed by best part decoding, which is Viterbi decoding, or by optimal CTC decoding based on the application of the forward algorithm to a tree-structured representation of all possible output strings. Some caveats: the blank structure that we just showed is just one possible way of dealing with repeating symbols. There are other ways which we won't get into. The blank structure happens to be very nice and convenient and gives you a very simple way of dealing with the problem, so which is why it is most popular. There are various variants. You could have, right now, the model uses just a single blank to represent the nothing happens here event. Anytime you see a blank, you know there's no symbol being produced at that location, right? But you could actually, because blanks fill in the gaps between symbols. So when you have blank, blank, blank A, that collapses to A. When you have blank, blank, blank B, that collapses to B. The blank in the two cases is the same. You could actually have symbol-specific blanks, in which case you'd be doubling your vocabulary. The decoder itself, or the model itself, can use bidirectional recurrent networks to compute the probabilities. There are various other variants possible. the most common models actually use bidirectional networks to compute the probabilities. CTC applications, they're used in various problems like speech recognition, speech goes in, phoneme sequence comes out, or you can even make it produce spelling, character sequences could come out, handwriting recognition, many other such setups. So here is a typical instance. Recurrent networks with LS teams can be used to perform speech recognition. The input is going to be a sequence of audio vectors. The output can be a phonetic label for each vector, or you can, instead of having just phonemes, you can directly output characters or even words. There are various other variants. Now, all of this was still with, remember, when we started speaking of sequence to sequence models, we said there were two cases. One was where the output was order synchronous with the input. There's a second case where the output need not be order synchronous with the input. An example is machine translation. So we've dealt with the order synchronous problem so far, where the output occurs in the same order as the input, and the number of output symbols is less than the number of input symbols. So you have the notion of aligning the output to the input. In the second case, like machine translation, where the number of symbols in the output can be greater even than the number of symbols in the input, and there need not be an order correspondence between the output and the input, this technique clearly cannot be applied. We will need a somewhat different model, and we will talk about this in the next class.